Okay, so now we are getting into simplifying, adding, and subtracting complex numbers. Complex numbers are including that imaginary unit I, which is the square root of -1. Okay, so where you used to not have a solution to an equation like x squared plus 25 equals 0. That's not dots, it's not factorable. If I make that x squared equals -25, when I take the square root, I remember I have a plus or minus solution when you take a square root. The square root of -25 will break down to be the square root of -1 times the square root of 25. The square root of 25 becomes 5, and the square root of -1 becomes I. Okay, so that's the purpose of having this imaginary unit. So we're going to start by simplifying, and then we're going to do some operations with these complex numbers. Notice that they're in what we call A plus BI form, and you're really going to pretty much see an overlap of stuff we talked about during radicals and then stuff that we talked about during polynomials with a little bit of calculator stuff thrown in there. So if I have to simplify something like 5 square root of -20, I'm going to make that square root of -1, okay, multiplied by 4 times 5. I still want to do the thing where I'm looking for the biggest perfect square that goes into 20, and I also have that -1. So I'm going to pull that -1 to the outside to come out to be an I. That 4 comes onto the outside to be a 2. Remember, all of these are getting multiplied by each other. Since I didn't circle the 5, that radical 5 gets left over. And then I finish simplifying by multiplying 5 times 2 to become 10. So 10I radical 5 is my solution for that first one. That's my simplified version. Again, it's basically simplifying radicals just like you did before with this additional component of pulling the I out of that radical from the square root of -1. All right, so now we get into some operations with multiplying or raising to powers, adding, subtracting. Remember that if you have something like -4i to the 8th, it's basically like -4i times -4i times -4i. You need to make sure you do this as -4 to the 8th and I to the 8th using exponent properties. So -4 to the 8th, pretty big number. Make sure you use parentheses when you type that in your calculator. -4 to the 8th comes out to be this huge number, 65,536. Okay, this I to the 8th you can also do right in your calculator. If you look right here above the decimal point, there's actually an I button. So you do second I raised to the 8th. Now you'll notice that in my calculator I get this kind of weird like E thing. It's a round off error. It basically means I have 1 plus 2 times 10 to the -13th I. Okay, that's basically 0. If I want to see this in a little bit of a cleaner way so I don't have to worry about this round off error, I'm going to hit math, I'm going to go to number, I'm going to go to I part, and I'm going to retype in that I to the 8th, and it gives it to me as a nice clean answer. I don't know why it doesn't automatically do that for you, but it just again, this is an imaginary unit, there's some round off error, this just kind of cleans it up. So I have that 65,536 times 1, which ends up coming out to be 65,536. Okay? So then we get into adding and subtracting. Adding and subtracting is literally going to be just like adding and subtracting polynomials. If I'm adding two terms together, I technically don't need these parentheses. I'm just going to be combining like terms. Okay, so what are my like terms? My 2 plus 4 adds up to be 6. 3i plus -6i adds up to -3i, and that's it. That's my final answer. You can easily check yourself, by the way, by typing this in. 2 plus 3i. Oopsies, 3i, plus, and again, technically I don't even need the parentheses, I'm just doing it for emphasis, 4 minus 6i, that adds up to be 6 minus 3i, just like we got when we did it by hand. If it happens that I'm subtracting, remember that essentially you want to do keep, switch, change, or distribute that -1 in the second parentheses. So this becomes 8 plus 4i, this becomes -2 minus I. I can once again combine like terms. 8 minus 2 is 6. 4i minus I is 3i. Again, you generally want to write your answer in what we say is A plus BI form, where you write the real component first and then the imaginary component second. Okay, getting into multiplying and dividing complex numbers. Again, you're going to see a lot of overlap with stuff that we did during polynomials, but you're also going to see a little bit of overlap with radicals. Once again, remember that I is equal to the square root of -1. So an important thing that's going to come up as we do this multiplying and dividing is that I squared, it's the square root of -1 squared. Remember, the square root and the squared cancel each other out, so that's how you find out that I squared is -1. Okay, so we're going to have to make sure we simplify that as we eventually start doing our multiplying and dividing problems. Okay, first things first, when I have a binomial raised to a power, it's very important that you remember that you really have to FOIL or use box method to multiply that out. It's not just 8 squared plus I squared. So I'm going to use the box method, and as I do this, I'm going to treat it kind of like I did during the radicals unit, where I'm going to try to make the bottom right-hand corner box a little bit bigger than the other boxes, because that's where most of the simplifying is going to happen. I have 8 plus I multiplied by 8 plus I. 8 times 8 comes out to be 64. 8 times I is 8I. 8 times I is also 8I. I times I is I squared. And as I just said, I squared is equal to -1. Just like during radicals, you're going to add along your diagonals. 8I plus 8I adds up to be 16I. 64 minus 1 is 63. Again, you want to have your answer in what we say is A plus BI form. So I'm going to put the real component first, plus the imaginary component, and there is my final answer. Similar to what we did during adding and subtracting, you can also check yourself by plugging this in. 8 plus I to the second, and you can see right there 63 plus 16I if you want to be able to check yourself. With question number 2, I'm going to do the same thing. I don't know if you recognize this, but these are what we would refer to as conjugates. They are the same parentheses, same exact numbers and everything, but with an opposite sign in the middle. And there's going to be something special that happens when I multiply these conjugates together. So similar to the last problem, I'll try to keep the bottom right-hand box a little bigger than the rest. 4 minus 2i, 4 plus 2i, and now I multiply. 4 times 4 is 16. 4 times negative 2i is negative 8i. 4 times 2i is regular 8i. 2 times negative 2 is negative 4. I times I is I squared. Careful in that bottom right-hand corner box. That's where most of the mistakes end up getting made. So this is really negative 4 times negative 1, which is really a positive 4. As I add along this diagonal, you're going to see that this adds up to be 0. Not like the last one. 8i plus 8i was 16i. This is negative 8i and positive 8i, so that adds up to be nothing. Then I add along the next diagonal. 16 plus 4 is 20. And notice that when I'm finished, I have no I term. Conjugates are special because when you multiply them, they multiply to become a regular number, okay? There's a regular whole number, not a complex number anymore. There's no imaginary component. Why are conjugates important? When you are trying to rationalize a fraction that involves I in the denominator, remember that I is really a radical, and we can't leave radicals in the denominator. I'm going to have to use the conjugate to turn the denominator into a whole number. So this 3 plus 5i, I'm going to multiply the top and bottom of this by the conjugate of the denominator. The conjugate would be 3 minus 5i, the same parentheses, but with an opposite sign in the middle. Okay, in the top, I can just distribute 1 to each of those terms, so that's going to become 3 minus 5i. But to get the bottom part, I'm going to have to FOIL that out. So I'll just do that off to the side. Okay, so I'm doing 3 plus 5i times 3 minus 5i. As I said before, when I'm done with this, because I'm multiplying conjugates, this should turn out like the last one, where it comes out to be just a whole number. So this is 9, this is 15i, this is negative 15i. Negative 5 times positive 5 is negative 25. I times I is I squared. Negative 25 times negative 1 is a regular 25. As I add along my diagonals, these add up to be nothing. 15i minus 15i is 0. 9 plus 25 is 34. So 34 becomes my denominator. You can leave your answer like this, 3 minus 5i over 34. You may see some answers sometimes expressed like this, 3 over 34 minus 5 over 34i, because technically that's A plus BI form, but I would be absolutely fine if you left it as 3 minus 5i over 34. For the last question, number 4, we're doing the same thing we did in the previous problem, but sometimes people get confused as to like what conjugate I should be multiplying by. It's the conjugate of the denominator. So my denominator being 4 minus I, I'm going to multiply by 4 plus I to both the top and the bottom. By multiplying by the same thing on the top and bottom, I'm multiplying technically by 1, so I'm not changing the value of these expressions, and I'll be able to turn that bottom multiplier into an actual just regular number, like in question number 3. So this time, because we have to do FOIL twice, I would do a FOIL box for both the top and the bottom. So that way, you keep yourself nice and organized and you remember what's supposed to go where. In the top, you're doing 2 plus 3i. and you're multiplying that by 4 plus I. And in the bottom, you're doing 4 minus I multiplied by 4 plus I. So as I multiply, 4 times 2 is 8, 4 times 3i is 12i, 2 times I is 2i times 3i is 3i squared, or 3 times negative 1, or really negative 3. Remember, you're adding along your diagonals. 12i plus 2i is 14i, 8 minus 3 is 5, and when you put that back in your numerator, you want to put it as a plus bi form. So 5 plus 14i. As you multiply your conjugates in the bottom, again, you should end up with a regular number. So 16 minus 4i plus 4i. Positive times negative makes negative I squared. Negative, negative 1 comes out to be positive 1. As I add along my diagonals, I have no i's left. That was the point of the conjugates. And 16 plus 1 comes out to be 17. As I said before, you could split them if you prefer to put it in a plus bi form like this, or look out for this as an equivalent form for this answer, but this would be fine if you were giving me an answer like this. Okay, so now we're talking about discriminant and the nature of the roots. And what this is referring to is when you have a quadratic graph, what kinds of roots, in other words, what kinds of zeros do you have with regard to the way that these, quadratics cross through the x-axis? So for example, you could have a quadratic that crosses through the x-axis at 2 points. If those points are nice, like whole numbers, or nice fractions like 3 and 5, or 1/2 and 7, or something like that, that's what we would refer to as rational roots. So this is 2 places. They are not equal to each other, unequal, and they are rational because they're whole numbers. If instead of being whole numbers, they were weird values like radical 3 and radical 18 or something like that, that's when I would have irrational roots, but I still have 2 real places that are unequal to each other where this graph crosses through the x-axis. Then I also have a situation where I have this graph only touching the x-axis at 1 point. We can either call that at 1 point, or we could say that it's actually 2 roots that are equal to each other. The fact that it's really touching the x-axis, though, those are going to end up being real roots. And then finally, the last situation that we have is a graph that is completely above the x-axis. It does not touch the x-axis at all, so that's when we would say we have imaginary roots. It does not really touch the x-axis. So how we're going to figure out what kind of roots that we have, which a lot of times we use to determine what's the best method to solve this quadratic equation, we're going to use something called the discriminant. The discriminant is the part of this quadratic formula that's underneath the square root, b squared minus 4ac. When we evaluate that, we're going to think about what happens when I take the square root of that value, and that's going to tell us if we have real values, or rational, or irrational, or imaginary. So I want to first go through, what does it mean if I have any of these discriminants? What does it mean if you have a discriminant of -5? So whenever you do a discriminant, next to it I want you to write, think square root of -5. If I take a square root of a negative number, we just talked about that in the previous couple lessons, that's when you're going to end up getting imaginary solutions. That means you have imaginary roots, so you have a situation like the third one where I have a parabola that would not be crossing through the x-axis at all. Then I have a discriminant that comes out to be 0. So imagine I'm evaluating this, I get the square root of 0, so I think, what happens when I take the square root of 0? Well, the square root of 0 is just 0. It doesn't come out to be a positive, negative version, it just comes out to be that 0. In this case, that's a real value. The only kind that comes out to be imaginary and negative. Okay, those are going to be rational values because I'll be able to express them as fractions. And this is the one situation when you'll have equal roots. Really, it's going to look something like this. It's going to look like one root to you, but we consider that to be 2 values that are technically equal to each other. All right, so then I get into something like 36. If I have a discriminant of 36, again, you're talking about the part that's under that square root. So think about what happens when you take the square root of 36. Well, that's a real value because it's a positive value that's under the square root. If you take the square root of 36, think about how that would be something like +6 and -6. Those are unequal values, okay? And they are rational because of the fact that when you square root 36, it comes out to be a whole number or a nice fraction. Last but not least, I have 45 as a discriminant. So what happens if I take the square root of 45? Well, it's going to be a real value The only kind that comes out to be imaginary is the one that's negative. This time though, square root of 45, 45 is not a perfect square. That's going to come out to give you some weird decimals, so those would be irrational solutions. And if I take the square root of 45, I have a positive or negative version of that, so that's how I still end up with unequal solutions. So basically what you're going to be doing in this lesson is calculating b squared minus 4ac. Make sure that your quadratic formula is in standard form, ax squared plus bx plus c equals 0. That's how you can make sure you have the right ABC values. And then once you calculate your discriminant, you think about what happens if you're going to take the square root of that and use that to determine the nature of your roots. So if you take a look at number 1, I have 9v squared plus 2v equals 0, so it's almost in standard form, but I'm missing that c value, so I may want to think of it as 9v squared plus 2v plus 0 equals 0. My a value would be 9, my b value would be 2, my c value would be 0. When you calculate the discriminant, you are calculating b squared minus 4ac. Okay, so b squared minus 4ac would be 2 squared minus 4 times 9 times 0. As I simplify that, I would probably say, so you don't make mistakes, because this is usually where people make mistakes during quadratic formula anyway, I would type that right in. 2 squared minus 4 times 9 times 0, and that comes out to be 4. So that's the actual value of the discriminant. So when it comes to doing the nature of the roots, what I want you to do is I want you to think, what happens when I take the square root of 4? Okay, when I take the square root of 4, am I getting a real or an imaginary value? It's a positive number. Those are going to be real roots. Okay, when I take the square root of 4, am I getting whole numbers, like nice fractions or nice whole numbers, or am I getting weird decimals? 4 is a perfect square, so that means that those are going to be rational values. And finally, whenever it's a positive number, you're always going to get unequal solutions based on the fact that technically you're getting positive 2 and negative 2 when you take the square root of 4. Okay, so that's my discriminant, and those are the nature of my roots. On to question number 2. I have to get this in standard form, so I'm going to add 7 to both sides. So negative 4x squared minus 4x minus 1 equals 0. So this gives me a equals negative 4, b equals negative 4, c equals negative 1. So I start with my discriminant. Okay, so that's again b squared minus 4ac. So that's going to be negative 4 squared, so be super careful to make sure you put that in parentheses, minus 4 times negative 4 times negative 1. So in my calculator, negative 4 in parentheses squared, super important because you're going to get a different value if you don't use parentheses. Minus 4 times negative 4 times negative 1. As I calculate that, that comes out to be 0. Okay, so that's a situation where I have a discriminant with a value of 0. And then in the nature of the roots, okay, I want to think what happens when I'm taking the square root of 0. Am I going to get a real value? The answer is yes. The only time it comes out to be imaginary if it was a negative value. Are they going to be rational? Yes, because 0, the square root of 0 is going to be 0, which is a rational value. And this is the only situation where you're going to end up getting equal roots. So if I graph this parabola, it's going to probably look something like this example here, where it's just touching the x-axis at a single point. Okay, last but not least, I have x squared minus 5x equals 2. Get this equal to 0. So I have x squared minus 5x minus 2 equals 0. Okay. You know what? I want to change this one up a little bit. I'm going to make it equal to, I'm going to make it x squared minus 5x plus 8 equals 0. Okay, I'm going to change that up just because I want to have a slightly different outcome with my solutions. So I start with my discriminant. Okay, you're doing b squared minus 4ac. This is an a of 1, a b of negative 5, and a c of 8. So that's going to be b squared, negative 5 squared, make sure you use parentheses, minus 4 times a times c. Okay, so as I evaluate that, use parentheses, especially around that negative 5. Minus 4 times 1 times 8 comes out to be negative 7. Okay, so as you do the nature of the roots, I want you to think what happens when I'm taking the square root of negative 7. So the fact that when I take the square root of a negative, I don't get real values, this means that the nature of the roots is that they are imaginary. And if I graph this parabola, this means this parabola is not going to touch the x-axis at all. Okay, so again, you calculate discriminant, and you think about what happens when you take the square root of that number, and you use that to figure out what your nature of the roots come out to be.